In this talk, we will talk about verifying labels. So, what do I mean with verifying labels? The relationship between a sample and a label in machine learning is central. We call this SL mapping for this talk. You can find this natively in labeled datasets, which you use for training a machine learning model. But you can also find this in trained models, especially when you look at the input sample and the output of the model, which is the prediction. They also form a mapping between a sample and a label. So our whole talk goes around the question, are these sample label mappings reliable or not? So why shouldn't they be reliable? One example would be a poisoning attack, where a regular model just outputs normal predictions and benign predictions for input sample, but an adversary can of course change the input sample. For example, add a trigger. You can see here a yellow square as a trigger, which might cause a misprediction in the machine learning model. So such a misprediction is then a false sample label mapping. Such sample label mappings, false sample label mappings, can either be in the labeled dataset if an adversary poisons the dataset, but you can also find it in the trained machine learning model if this model is trained on a poisoned dataset. So we designed a method called label trust, which can evaluate those sample label mappings. This is a general tool, but besides of that, it can be used in different use cases. In fact, those two scenarios that I told you, you can have two use cases. One is dataset cleaning and one is confidence scoring. Dataset cleaning is clear. You want to remove the poison from dataset. For confidence scoring, you want to provide a trust score for the prediction of a pre-trained model. So both of these things have the same underlying problem, the quality of the SL mapping, and our tool provides a score that is expressive and can be used directly for confidence scoring. And for dataset cleaning, we can filter the dataset when evaluating the score against a threshold. So the existing works from both domains have several downsides. For example, they rely on big datasets, either the complete dataset or also big clean datasets. They can also be specific to one model architecture or one model instance, one trained instance, or some confidence scoring works. They also don't consider poisoning attacks at all. But more importantly, we have the same underlying problem, but there's no unique solution to those two use cases. And this is what we tackle with label trust. So the principle of label trust is already clear. You take this sample label mapping, feed it into label trust, and you get the score, which you can then use for both use cases. Thereby, our system label trust relies on a small reference dataset with trusted samples, so clean samples. But other than other works, we only need 2 clean samples from each class, which is a bare minimum. This trusted or reference data set is created by a domain expert, so from a human being. For dataset cleaning, he can just sample labels from the poisoned dataset, see if those samples are poisoned or not, and feed them into the reference dataset. For the confidence scoring, we can do the same if we have access to the training dataset of the pre-trained model. If not, label trust can be provided by the model creator, or the model creator can provide some samples. If we don't have access to any data, we can just observe the input and the output of the model during production and use these sample label mappings, give them to the domain expert, and with those mappings feed the reference dataset. So we always have access to those. And we then use the small reference dataset to train a model that can essentially answer the question if a SL mapping is reliable or not. So you feed it with a SL mapping and get a quality score here. So this model essentially answers the question, is the provided sample really from the assigned label class? And this question is answered based on the knowledge that is within the reference dataset. So if some sample is not represented by other samples in the reference dataset, of course, the score will be low. So as a model architecture, we use CMS networks here. So in a CMS network, you can have a sample which consists of two data records, for example, 2 images. And first, you feed the first sample into a feature encoding subnetwork to create an embedding. Then you do the same with the second sample, and you use the same feature encoding subnetwork. Those 2 embeddings can then be compared by a decision network, essentially yielding a score or some similarity measure. So such a network can essentially answer the question if those two samples are similar. They can answer the question if both samples are from the same class or are from different classes. So how do we use this in label trust training? We have our small reference data set with our bare minimum of 2 classes. Perhaps we have more. We have visualized 3 or more here. And we use this data set to expand it to a CMS data set. Essentially, we build pairs of samples, either belonging to the same class or to different classes. And with such a data set here, we can then train the CMS network. And then this network can answer the question if 2 samples are from the same class or not. As we rely on relatively few samples, CMS networks are one instance of future learning. During inference, we then are presented with a sample label mapping. In this case, I visualize an adversarial sample label mapping where a bird is labeled as a dog. During inference, we then take the samples that we have here from the respective label class, dog in this case, and pair them with the input sample, a bird here. We will then feed these pairs into the CMS network and average the scores that we get for the different samples to get a final score. So this score can then either be high or low. For a high score, we say, okay, we have a clean sample, we have a high probability that this is benign because we have respective samples in the reference dataset already. If the score is too low, this can have various reasons. Either the sample is really poisoned, as in our example, and then it should be filtered out, or the knowledge can not be available in the reference dataset. And therefore, with these uncertain samples here that have too low scores, we give them to the domain expert again and make a human in the loop, refeed loop here. And either he filters them out if there's a poison sample, or he can increase the size of the dataset over time and feed new knowledge into it. Of course, we then retrain our CMS network, and over time, the performance of label trust will be increased. So now that you know how the overall system of label trust works, so we can feed it with 2 samples, and we can feed it with a sample and a label class, and then compare if we have seen such a sample in our reference data set, we come to the evaluation. So for the evaluation, we used, in this case, I visualized results for the MNIST dataset, but we used various datasets, which I will show later. First, we selected a reference dataset out of this complete dataset and expanded then the reference dataset to a CMS dataset again, pairing different samples. The size of the CMS dataset, we've chosen to make it as big as the original dataset. This is a hyperparameter of CMS training. You can use different settings here. Then we fed this dataset to the CMS network. We used the ResNet 18 for the feature extractor and 2 linear layers for the decision network. We used binary cross entropy as a loss and poisoned 10% of the data of the original dataset. Then we applied a threshold for our score of 0.99. The results that I will present will show you results for a reference dataset that contains 2, 5, 10, 15, and 20 samples for each class within the reference dataset. So if we have MNIST with 10 classes, 20, 50, 100 samples, and so on. The first thing that we did is we took the MNIST test set and created a CMS dataset from it. So again, we formed some pairs, and we looked at the accuracy. As you can see, the accuracy increases with more samples in the reference dataset, which of course is expected. The more samples you have in your reference dataset, the more knowledge is embedded in there, and the higher the quality of the classifier of the CMS network is. So therefore, we can see that our intuition that this human in the loop increases the performance is true. Then we looked at direct sample label mappings from the MNIST dataset. So we don't form pairs now, but we take the samples and check if the assigned label is true. So we can see again that the accuracy increases over time. And first, there are some samples that are rejected that have too low scores. And over time, those samples are also recognized as the knowledge in the reference dataset is increased, so we can see that the false rejection ratio decreases over time. This again shows us that adding new samples to our reference dataset increases the performance. Lastly, we looked at poison data. So each sample that we test now is a poison sample. We report the average score, which we expect to be low, and the true rejection ratio, so this is expected to be high. So as we can see, the average scores are really low here. And already in the first iteration, where we only have 2 samples from each class in the reference dataset, we can detect 100% of the poison samples. Over time, we can only detect 99 point something. There are some samples that are not detected, and those are samples we embedded a red trigger here, where we can see a red car, and the trigger is right on the car. So yeah, you cannot do anything about that, but the performance is still really, really good. So I told you that we tested different setups. So you can see that we use different data sets, also a colored data set, different backdoors, several models for the CMS feature extractor, and also different thresholds. The experiments are consistent in those setups. I only present this one table, but the experiments are consistent. Now we come to the different use cases that where we can apply label trust. First, to dataset cleaning. So for dataset cleaning, I show examples where we have a reference dataset consisting of 10 to 35 samples per class, meaning that a domain expert checked 10 samples per class, meaning 100 samples, or 350 samples, because we have 10 classes again. So as you can see, the clean samples, the samples that were identified as clean, increases over time, which is in line with our intuition. And as the domain expert only checked 350 samples here, we can say for checking these 50,000 samples, he only needed to check 0.0058% of the dataset, which is, of course, very good. In parallel, of course, the samples that are filtered and not considered as clean decrease over time. Within those 10,000 samples that are left here, we have nearly all of our poisonings. So we have 99.7% of the poisonings, and we have 4,300 samples that are falsely filtered out. Within those falsely filtered out samples, there are also some that have really low quality and shouldn't be embedded in the training. So as you can see here, we already filtered out all the poisonings, and this is done already after the first iteration. So if we use the samples that are considered clean after the first iteration, we already removed the backdoor. Yeah, the accuracy values go along with the ones presented in the previous slides. For the confidence scoring, we have a scenario where we have 10 samples in the reference dataset, and we compare the results for benign test set with the results of a poison test set. And as you can see, the values, the confidence score values, are really lower for the poison dataset, and this shows that these false mappings reliably yield low scores. And as the difference between those scores is relatively high, we can clearly identify the poisonings. When we apply a threshold like 0.99, this would barely yield any error. To this threshold value, I want to add that our system is not dependent on a threshold value. The threshold value is chosen by the user, depending on what he wants to know. If he wants to know which samples are really for which samples the system is really highly confident, or for which sample it is really not confident. You can also select the threshold of 0.5, but there is barely a question that the user can ask that justifies this threshold. So normally you have a high threshold or a low threshold. I presented the results for 0.99 as it is intuitive for dataset cleaning. So to sum up the talk, we have sample label mappings that are central in machine learning in different use cases, especially for dataset cleaning and confidence scoring. And existing works in those domains have several downsides, especially there's no dual-use tool, even if we have the same underlying problem. And sometimes they rely on complete untrusted datasets or big clean datasets. They can be specific to a model or architecture or a model instance, and some confidence scoring works don't consider the poisoning attacks in their evaluations. Therefore, we present label trust here, a system that can score sample label mappings based on the information contained in a reference data set. It can be used for 2 use cases, and we only need a few trusted, clean samples as we apply future learning with the CMS network. Further, the system can be enhanced over time as we have a refeed loop that can improve the performance over time. So that is everything from my side. I'm now happy to take your questions. Thank you.